In this video, I will solve some NEET PYQs from the topic Mechanical Properties of Solids. These questions are based on Young's modulus of elasticity and Bullk modulus of elasticity. Timestamps are given in the description box. You can watch parts of video if you are running short of time. I will discuss some 5 questions. This is the first one. You can read it. The following 4 wires are made of same material. Which of these will have largest extension when the same tension is applied? 4 options are given. Length is changing, diameter is changing. Young's modulus is defined as stress by strain. Stress is force per unit area. Here is tension divided by area. And strain is change in the length by original length. You have to find the largest extension. So that means you have to find delta L. Bring Y to this side and L will go up. So the extension is more, the initial length is more, and also the stretching force is more. So tension is same for all the 4 cases, and also the material is same. That means Young's modulus is same. Tension is same, Young's modulus is same. So this is constant. So for the 4 cases, you have to compare L by A. A is the cross-section area of the wire, which is a circular disc here, which is pi by 4 d square. So you have to compare L by d square for all these 4 cases. First case, the length is 100, diameter is 1 mm square. This has to be compared with 200 diameter square. Third case, length is 300, the diameter is 3 mm. And then the fourth case is 50 length, diameter is 0.5. The dimension of all these quantities, or the units of all these quantities, is centimeter by mm square. There is no need to convert the units because it will give a factor that will get cancelled. So no need to waste time in converting the units. So this one, the first one is 100. Second one is 100 by 2, 100 by 3, and 50 by 0.5 square is 0.25. 1, 2 will cancel, so it will be 100 by 2. 1, 3 will cancel to make it 100, 100 by 3. And 0.25 is 1 by 4. So the 4 will go up, so this will become 200. So 100, 50, 100 by 3, 200. So this is the maximum value. So fourth case, the extension is maximum. T is the correct answer. This is what I explained here. Young's modulus is stress by strain. Force per unit area, force is tension by area is pi by 4 d square. Strain is delta L by L. From this we get delta L proportional to L by d square because Y is same for all the 4 cases, material is same, and pulling force tension is same for all the 4 cases. So the only variables are L, D, and delta L. So delta L is proportional to L by d square. So we have to compare this thing for the 4 cases. So cancelling zeros and simplifying, we get the fourth case as the maximum value. And the units are centimeter by mm square. There is no need to convert because it will get cancelled. Whatever is the factor, conversion factor, it's same for all 4 cases, which will get cancelled. Let's move to the next question. with the ratio of diameters, lengths, and Young's modulus of steel and copper wires shown in the figure are P, Q, and S respectively, then the corresponding ratio of increase in their lengths would be. Four options are given. So steel wire, copper wire. So this mass 2m, 5m. So the steel wire will have a load of this entire thing below it. So that is 2m plus 7, 5m, there will be 7m. We can neglect the mass of this copper wire. By this copper wire, we will feel the weight because of this bottom mass only. Because this is just like a support. Only this 5m mass will pull this copper wire. You can pause and attempt this question. So Young's modulus of first one, steel, is stress, which is the force that is pulling this wire, which is 7m. Weight is into G by cross section area of the steel wire, and then elongation of steel by the length of steel wire is a strain. For copper wire, the load is only 5m. Weight is into G, and cross section area is AC. Let the elongation be EC and the length be LC. So you find the ratio of increase in the length. So ES by EC. Take ES on this side, bring YS here. Similarly, EC on this side and YC here, and divide these two. So that will give ES will go here. So ES by EC. MG will cancel. 7 by 5. A is at the bottom. So AC by AS. And then LS will go up. LS by LC. And then YS is coming down. Simple manipulation. Divide these two after taking this E on the left side. And the ratio of diameters is given. Area is same as pi by 4 d square. So area ratio is same as diameter square ratios. So this is 7 by 5. Ratio of diameters is P, but it is steel by copper. So steel is down. So it will be 1 by P square. And the second ratio of lengths, which is Q, steel by copper. Third ratio is Young's modulus, S, steel by copper. Steel is down. So it will be 1 by S. So this is 7 by 5, Q by P square S. C is the correct answer. This one I explain here. Young's modulus of steel is force by area, and then by strain is the change in the length by the original length. From this I get the elongation for the first one, that is steel, 7 mg L1 by A1 to YS by YS. So from this I can write E2 as, instead of 7 mg will be 5 mg L2 A2 by YC. So taking this ratio E1 by E2, I can get the answer as option C. Let's move to the next question. This is the next question. Two wires A and B of same material, lengths are in ratio 1:2, diameter are in ratio 2:1. If they are pulled with the same force, then the increase in length will be in the ratio. This is similar to the previous question, except that instead of ratios in terms of P, Q, and S, they are given the numbers. So exactly same question, concept-wise. So Young's modulus of the first wire is pulled by the same force. So F by A1, elongation 1 by L1. And the second wire is also same material. So the same wire will be equal to the second wire. Case force is same, cross section area is different, elongation is different, and the length is also different. So equating these two, or take E1 here and E2 here and then divide both of them. So E1 by E2, F will cancel, will become E2 by A1, and then L1 will go up, L1 by L2, F will cancel, Y will cancel, E is going this side, so A and L are there, so only this much. And area ratio is same as the square of the diameters. Diameter ratio is low. Area is pi by 4 d square, so this is nothing but d2 square by d1 square. So ratio of diameters is 2:1, and 1 is at the bottom, so it's 1 by 2. The first diameter is bigger. The first diameter is here, so it will be 1 by 2 into length ratio 1 by 2. It's 1 by 8. C is the correct answer. Young's modulus, stress by strain for the first wire, F by A1 and U1 by L1. Second wire, Young's modulus is same because same material, and force is also same, so same F. A2 is different, and elongation E2 and L2 are different from the first one. So from here, I can write E1 by E2 as this ratio. So these values are given. Diameter ratio is given, so then I can get the area ratio as square of that diameter ratio. Option C. This is the next question. When a block of mass is suspended by a long wire of length L, the length of the wire becomes L plus L. The elastic potential energy stored in extended wire is. Energy can be stored in a spring when it's stretched or compressed. So this wire is like a spring only because it can be stretched and it can also be compressed. So it is getting stretched, some energy is getting stored in it. The formula for energy per unit volume which is stored in this wire is half into stress into strain. This formula I can straight away use. This formula comes from the fact that the energy stored in the system equal to work done on the system. To stretch the wire, some work is required to be done on the wire, which is integral F ds. So if you do this calculation, you'll get this formula. But that's not required for this question. You just have to use this formula. So half stress is force per unit area, and force is because of the mass mg by area. Strain is the change in the length, which is small l, by the original length, capital L. And this A into L is the volume of the wire. So we can cancel B with A into L. So from this, you get the energy stored in the wire, half mg L. C is the correct option. Energy per unit volume, the formula is half stress into strain. Stress is force per unit area, force is equals to mass in hanging, so mg by A. The strain is the change in length, which is small l, by the original length, it's L. So this one, and you have to use the volume of the wire as A into L. This is the next question. The bulk modulus of a spherical object is B. If it is subjected to uniform pressure P, fractional decrease in the radiuses. You can pause and attempt this question. Bulk modulus, like Young's modulus, is defined as stress by strain. Stress is force per unit area, but in this particular case, stress is same as pressure. And strain is the measure of deformation. In the case of a wire, it is the change in length by the original length. But in the case of a 3D object, the measure of deformation is change in volume by original volume. But since here the pressure is a compressive force, the volume will decrease, so delta will be negative. To make this thing positive, you have to put a minus sign here, because it is a compressive stress. And volume of a sphere, spherical object, 4 by 3 pi r cube, where r is reduced with the sphere. So you need delta V, which is same as dV. So when the thing is getting compressed, R will change and V will change. So the variables are V and R. So differentiate both the sides. dV equal to 4 by 3 pi 3r square dr. 3 will cancel. So 4 pi r square dr. Is dV. What is equal here is dV by V. So divide this by this. So dV by the fractional change in the volume is 4 pi will go r square and then r cube shall become 1 by r and then dr. And this 3 is there. So 3 times dr by r. Left side is dimensionless, volume per volume. Right side also dimensionless, length by length. And there is a factor 3 because of this 3. So putting this thing here, bulk modulus is pressure by minus dV by V. So that is minus 3 by r dr. When it's getting compressed, dr will be negative. So this will cancel this negative and make this thing positive. So this minus sign is correct. So from fractional decrease in the radius, so that is dr by r, we can take it here with the minus sign. It will become 3 by 3b. dr is negative, so this minus dr is a positive quantity. So this fractional decrease in radius is a positive quantity. So this minus sign should be attached to this dr. So the answer is C is the correct answer. This is what I explained here. Bulk modulus is defined as stress by strain, but in the case of 3D object, the stress is pressure, and strain is measure of deformation. For a 3D case, it is change in the volume by original volume. And since the compressive pressure, dV is negative, so to make this thing positive, this minus sign is required. Volume of a sphere, 4 by 3 pi r cube. So when the thing is getting compressed, R will change and the volume will change. So the variables are V and R. Differentiate both the sides. dV equal to 4 pi r square dr. So from this, the fractional change in the volume, divide these two, is thrice the fractional change in the radius. So using this thing here, So dE by R is 3 times this one. So this minus sign, I'll put it here. So this minus dr by R, this P by dV. So since the things getting compressed, dr is negative, so this will make it positive. That's equal to P by dV. Correct option is option C.